So we left off with complex numbers, like I said, and that was basically we did some working with I, the complex unit, right? And if you are unfamiliar with those or you weren't here last time, you really need to go back and check that out. This was a little interesting thing on the side regarding, at least I thought it was interesting, regarding a very strange looking answer. And we're seeing that answers on the calculator, when you raise them to high powers or very precise calculations or something, sometimes they're a little bit off in like the 6th or 7th decimal place, something like that, right? And this turns out to be off in the like 10th decimal place, right? I should say, if you were going to write this out, just one more thing to write here, minus 1.9 times 10 to the negative 10th. That would be, are you ready? Minus 0.00000000019. That's what the decimal would be. Very small. The calculator here is trying to say 0 plus or minus, excuse me, I, which is minus I. That's what the calculator is trying to say there. So if you want to decrypt something like that on your calculator, you need to know a little bit about scientific notation. Right? Complex numbers use the complex unit. So complex numbers are of the form, we always say Z for a complex number, typically ZW, those, we don't use X usually, but ZW are typical ones. A plus BI. Now I is the critter we just saw. A and B are ordinary real numbers. So A and B come off the number line somewhere. And what you have is this is the real part, and this is the complex part. Right? If A is 0, you just have a purely complex number. So that number will not be on the number line. And to jump down here, I'm going to jump down to letter B down here is of that form. Right? There's nothing to do in this example. There's no work to do. These are just examples of complex numbers. So minus 2I is really 0 minus 2I. And using up here, this is the A, and minus 2 is the B. To put it in the form A, some number, plus some multiple of I. Well, this happens to be 0 plus minus 2 times I. So in this example, B is minus 2. Here's another one, 3 minus 2I. Both of them have minus 2I. Maybe I know. I shouldn't. But 3 minus 2I, this has a real and complex part. It's still not on the number line, though. It's not on the number line. Okay. And so when we were talking about quadratic equations previous days, I mentioned that all quadratic equations have 2 solutions if you count multiplicities. And if a discriminant is 0, excuse me, negative, what I was about to say is true, it just wasn't relevant. If a discriminant, the part under the square root, b squared minus 4ac is negative, then you have 2 complex solutions to that quadratic equation. And you recall that the graph will entirely miss the x-axis. Anytime it hits the x-axis, it's kind of hitting the number line. And so if it hits the x-axis, those are real solutions. And you can have either 2 or 1 of those of a multiplicity 2. We'll get into multiplicities down the road. All right, well, let's work with this. Actually, before we do, we got to talk about the conjugate. Now, you've had conjugates before. You should have had. You had stuff like, if you had 1 minus square root of 5, you learned that its conjugate was 1 plus square root of 5. And what you most commonly did with these is that if you had something like that in the denominator of a fraction, you were told to rationalize by multiplying top and bottom by the conjugate. Why is the conjugate a good thing? When you multiply a fraction on the top and bottom, if you FOIL this out, 1 plus 1 is 1. Did I say plus 1? 1 times 1 is 1. 1 times square root of 5 plus square root of 5. Minus square root of 5 times 1 is minus square root of 5. And then minus square root of 5 times plus square root of 5 is minus 5. And so you multiplied something like this by the conjugate, and the square roots of 5s canceled. Now, whenever you did that, you had to multiply top and bottom of the fraction. You couldn't just multiply the bottom. Because when you multiply top and bottom of a fraction by the same number, you're multiplying by 1. So if I have a fraction, multiply the top by 2 and the bottom by 2, I've multiplied by 2 over 2, which is 1. So this gave you minus 4. And that usually was in the denominator of an expression, and you got rid of the square root in the denominator. Now, what I want to call your attention to here is a fundamental property of binomials. When you multiply pig plus cow by pig minus cow, the same two numbers, just with a minus in it, you get pig squared minus cow squared. So I should put this over here somewhere. Like if you had a plus b times a minus b, this equals a squared minus b squared. That's a fundamental property. And if you FOIL this out, you'll see that the cross terms cancel. That's why. Just like here. We're about to use that is what I'm saying. We're about to use this property. Okay. Now, the advantage of a complex conjugate. Now, if you have a complex number, a plus bi, just like here, if this was a negative, it turned positive. So the conjugate of a plus bi is written z with a bar on top, a minus bi. You flip the sign of what's in the middle. So if it's a plus, becomes a minus, minus becomes a plus. Here, the b part was minus square root of 5. You flip the sign to get the conjugate plus square root of 5. And that provides you with this property that the cross terms cancel. Now, so the conjugate of a plus bi is a minus bi. Now, stop me if you're not getting that, if you have a question. Down here is why we do that. A property of the complex conjugate is this, that if you take a complex number and multiply by its conjugate in either order, so if I have a plus bi multiplied by its conjugate, a minus bi, in either order, you get a squared plus b squared. And it's always a plus in the middle. Now that should make you scratch your head a little bit. If you do too much, you'll wind up looking like me, right? Even somebody with a lot of hair like Jevin, he winds up looking like, no, just kidding. Oh, hope not, bro. Hope not. What happens here? If I have a plus bi times a minus bi, if I FOIL that out, if you notice, why is there a negative here and a positive here when I'm doing plus and minus the same thing? Why is that true? So I don't want this to be confusing with so-called regular algebra, right? This is complex, works a little different sometimes. So if I FOIL this out, I'm going to have f, outer, inner, last. By the way, I've said it before. If you learned a different way to multiply binomials, I'm aware of those different ways. FOIL is the most common method, but if you have a different way of doing it, by all means do it. I won't hold you to FOIL. But a times a is a squared. A times minus bi is minus a bi. Bi times a is plus a bi. And this last term, bi times minus bi. is b times b. That's going to give minus b squared. I times I is I squared. Okay, so we just standard FOIL, right? These buzzards cancel. And so I wind up with a squared minus b squared I squared. Well, that doesn't look like that yet, right? Now, and when we're doing this, by the way, we see how we multiply. You multiply with FOIL, just the same way as you did before. I squared, this guy is minus 1. We got that, see? So that minus 1 will flip this sign. And so that gives us our a squared plus b squared. Because this minus here cancels with that minus there. Minus signs cancel in pairs when you multiply, right? Okay? That is why this is true. Now, I could have just told you to memorize it. But just telling you to memorize something isn't usually my style. Okay? If you can explain it. And it turns out if you explain it, there's probably some learning in the explanation too. And so here we give our first illustration on multiplying complex numbers. They multiply like FOIL. And we're going to be doing a bunch of this. Any questions? We're going to be using this conjugate here again in a minute. Example. Find the conjugate of the following complex numbers. This is z. So a is 3, b is minus 2. So its conjugate is going to be z bar is 3 plus 2i. You flip the sign in the middle. W is minus 3i. What's the conjugate? I think the first thing you should realize is that minus 3i is 0 minus 3i. That's 0 minus 3i. So the real part of this, the a part, is 0. This is a purely imaginary, purely complex number. The a part is 0. But to get the conjugate, you flip the sign in the middle. So w bar is 0 plus 3i, or just 3i. All right? Stop me if you have a question. Don't be shy. Now, z times z bar. And we're going to use this z here. Z times z bar. Well, that is 3 minus 2i times 3 plus 2i we're multiplying a complex number by its conjugate. The cross terms cancel. So using our formula, this is our A, that's our B. The shortcut formula just says A squared, 3 squared plus 2 squared. Actually, it's going to be a minus 2 squared. Yeah. Because B is minus 2, right? And that gives me 9 plus 4, or 13. Notice z times z bar, when you multiply a number by its conjugate, gives you just a purely real number. Backing up a second, up here, a squared plus b squared, a and b are real numbers. So that's a real number squared. That's a real number squared. When you add them together, you get a real number. By the way, when you add them together, the real number may or may not be a square itself, right? 13 is not a perfect square. There are cases you will have that. Any questions on that? We're going to be doing this again in the next slide. Example. Here's two complex numbers. We're going to add, subtract, multiply, and divide now. And to tell you the truth, we've already done most of it. All right, so this is sort of bringing it together. All right, so z plus w. Z is 1 minus 2i plus w, 3 plus I. Now, if you want to do this quick, you just add the real parts and add the imaginary parts. But this will give you 1 minus 2i plus 3 plus I. Remove the parentheses. And you combine like terms. 1 and 3 are the real terms. Minus 2 and 1, there's a 1 right here, right? Right? So we're grouping these like terms. 1 plus 3 is 4. Minus 2 plus 1 is minus 1i. Right? This guy here. We're going to plug in with z equals, plug in with w equals. 4 times what z equals minus 2 times what w equals. All right, multiply things out. 4 times 1, 4. 4 times minus 2, minus 8i. Minus 2 times 3, minus 6. Minus 2 times I, minus 2. Group like terms. 4 minus 6. Plus minus 8 minus 2. All times I. That gives us a nice 10. No, I'm sorry, minus 2. And then minus 10. All right. Questions on that? Get a little stickier here. Z times W. Not bad, though. Z times W. Z, 1 minus 2i. W, 3 plus I. FOIL. 1 times 3, 3. One times I, I. Minus 2i times 3, minus 6i. Minus 2i times I, minus 2i squared. Three times 1. Minus 1 times that, minus 2 times 3, minus 6i, minus 2i times I, minus 2i squared. So, 3 doesn't have anything to pair with yet. Plus I minus 6i minus 5i. And then I have minus 2i squared. I squared, you notice the L term on FOIL gets the squared I. So that becomes a minus 1 every time. This part does it. So this little guy here becomes a minus 1. That turns that into a plus 2. So that's a plus 2. And that gives me 5 minus 5i. 5 minus 5i. It doesn't really look like either of the numbers it started with, right? So, right. Hard to see patterns between these two and the product. One more. Actually, one more on this slide, then we've got some more next slide. Next slide is the fun one. I know what you're thinking. Mr. Miller, I've been waiting 2 weeks for the fun one. Z times Z bar, that's Z, 1 minus 2i. Z bar, 1 plus 2i. Now I could FOIL that out. Oh, that's so right. Us lazy bottom-dwelling scum suckers know that this is A and that's B. And this is going to equal A squared plus B squared. So A squared is 1 squared plus B squared is minus 2 squared. That equals 1 plus 4 or 5. Again, a number, complex number times its conjugate is always a purely real number. No complex part to that product. All right? Did I mention you're going to have to do this? We have a homework tonight, actually, for this. I don't want to jump ahead. It's done. All right. This one's a little strange. But you'll see the point. There's a madness to my method. Answer from C. 5 minus 5i. Divided by W. 3 plus I. This is going to be 5 minus 5i. 3 plus I. See? That's W. Now, remember what we did a few minutes ago, where I said you'd probably seen conjugates before. And that is when you have something like that in the denominator. When you have a complex number in the denominator, what we're doing is we're dividing two complex numbers. Notice what we're doing here. Addition of complex numbers, subtraction, multiplication, division. It's the arithmetic of complex numbers. Now, what do you do? Well, we're going to multiply by 1. Never underestimate the power of multiplying by 1 or adding 0 in a strategic way. So we are going to pick a number that deals with this fraction in the denominator. And the number we're going to pick is the conjugate. 3 minus I. Now I can't multiply the bottom by 3 minus I. My bones are out of line. Top is also 3 minus I. So I have effectively multiplied by 1. Right? See that logic? So we're really not changing the value. We're simplifying. So what happens from there? Well, you remember fractions, you multiply straight across the top, straight across the bottom. 5 times 3, 15. FOIL. 5 times minus I minus 5I. First, outer, inner. Minus 5I times 3. Minus 15I. Then finally, lots of negatives here. Minus 5I times minus I. That is a plus 5I squared. Are we cool on that?
And we'd like to give us a special greeting to those watching on video over the weekend.
Okay, switch to decaf Miller. The bottom, well, I got something times its conjugate. Right? And so us lazy bottom dwellers, we can foil that out, but no, you don't foil that. So that's like so 90s, you know. We're going to use our property. This is 3 squared plus b squared, 1 squared.
That was easy.
Use that property. Well, how does this work out? Let's see. 3 squared plus 1 squared is 10. 15 doesn't have anything to go with yet, right? Minus 5I minus 15I is minus 25. And then this little dude here is a minus 1, right? So I really had 3 negative signs on my L term of FOIL up here. Because I had minus 5I times minus I. Those 2 negative signs canceled. But this I squared produces yet another negative sign. So up here I have a minus 5. And on tests and quizzes, that is where the mistake happens. Not flipping the negative, right? We're going to have that. 15 minus 5 now is 10. So I have 10 minus 20I divided by 10. But you don't leave it that way. Every answer in here you have to simplify. And no, I don't believe everyone can simplify them because I've seen too many simplifications. The simplification itself sometimes reflects further understanding. So here, I can split out that fraction, right? That equals 10 over 10 minus 20 over 10 times I. I can split out that numerator. 10 over 10 is 1. 20 over 10 is 2, minus 2 in this case. I. Does that look familiar? It was Z. Why should you care? To me, that's cool. Whoa. Why is that? Why should you care? Here. How should division work? If I multiply over here 3 times 2 and get 6, I have a product that equals 6. And if I divide 6 by one of these, I should get the other one, right? So, right? If I divide each side, 3 times 2 is 6. And I divide the left by 2 and the right by 2. I should get 3. The other one. Here, up here, answer from C. This is why I worded it weird like this. What was C? C was ZW. I didn't want to put ZW there because someone would say, oh, ZW, W just canceled. I wanted to show you how to do division of complex numbers. That was the goal of this particular part. But I also want to just point out that division of complex numbers makes sense just like the division of real numbers, right? If I take a product, 6, and divide by one of its factors, I get the other factor. So I took a product, divided by one of its factors, I got the other factor for an answer. So that is just my attempt to point out how division of complex numbers works like you expect division to work. And so we'll have to do that. We'll have to do this. Any questions on that? Oh, by the way, any questions? By the way, you can do this on your calculator. Yabba dabba do, right? Right over here. See this? Okay. So get out your, not that, get out your calculator. I don't have a calculator. But you do have a calculator. Or you have one coming post haste. Shake your head, yes. Start asking some of your teammates or whatever, or calculator. So let's, that was fun. That was a lot of fun there, right? Uh-oh. Yeah. Whoa. This calculator, this computer is freezing programs. Let's try this again. Clear. All right, decided to work. Good. Up here. I'm going to leave that for a second. I'm going to put this equation. You know what? I don't need to do that at all. Sorry. I don't have to do that at all. Let's do the calculation over here on the left, right here. This calculation here. 1 minus 2i. Right? You're going to do 1, left parenthesis. 1 minus 2. Remember how to put the I on the screen? Second decimal. Right parenthesis. Left parenthesis. 3 plus I. And just for fun, I'll remind us that your calculator will close any open parentheses at the end of the line, whether you want them closed there or not. Now, in this case, I would normally put a right parenthesis there, but just for fun, I won't. And that gives me 5 minus 5i, which is what we got. That's what we got in our part C, right? And now I'm going to divide that by 3 plus I. Take my answer, divide by 3 plus I. That is strange. Oh, I divided by 3 plus I. That makes no sense. What's happening? Oh. Okay. When the teacher screws up, it's a teachable moment for the class. This is my bad. Let me tell you why. Does anybody see what I did wrong here? The calculator is perfectly correct. I took my answer and I said divided by 3 plus I. It divided it by 3, then added I. It's orders of operation. So I divided my answer by 3 and added I. What I should have done is this. Let's start with our product again. What I should have done is divided by left parenthesis 3 plus I. And that gives me the other one, like it should. Right? So learn from my mistake. Very common mistake, as you see, sometimes I do it. Okay. All right. Any questions on that? So you have that down at the bottom right of your screen. All right. Money. Same stuff we just did, right? Same stuff we just did. And we even have here, see, so do Monday. Here's your answers. Try these on your calculator. Become familiar with those functions. Yeah, I've been around a lot of math departments. Number one reason, numero uno, essential skills. You're going to see essential skills a lot. Why? Because what we're doing is we're going through chapter R1 and 2. We're not in 2 yet. And we're doing only the absolute bare minimum of review from what you should already be familiar with. The only one I'll give a little slack on is that complex number stuff. Because, like I said, that used to be part of any Algebra 2 class. But these days, they're throwing out anything that's not on the ACT or SAT. It's pathetic. It's really pathetic. Right? And we wonder why some other countries are blowing by us in the STEM fields. Right? So anyway, intercepts. Intercepts. Okay. This is such a common hang-up. Right? Y-intercept, X-intercept. Okay. I'm only going to do this once because I'm old. How do you find the y-intercept of any function in the universe? Plug in 0. That's my exercise for the weekend. My phone's here somewhere.
It's right there.
Oh, okay, stay. Okay. Plug in 0, folks. That's how you get the y-intercept. Now, if you think about it, I have a function. And it looks like this. That's my function f of x. If I plug in 0, what do I get? Well, I'm plugging in the x, the value. When I plug in 0, I get, right? This is 0. You plug it in, you get the y-intercept. It's the value of the function when you plug in 0. Okay. How do you get the x-intercept or intercepts of any function in the universe? You solve the function equal to 0. So you set the function equal to 0 and solve. Why does that work? Because you set the function equal to 0. If y equals f of x, and I set the function equal to 0, that's y equals 0. What is y equals 0? It's the x-axis. So when I set the function equal to 0, I'm setting y equal to 0, and I'm finding the x values that make y equal to 0, which means the x values along the x-axis. How do you find the y-intercept of any function in the universe? Plug in 0. How do you find the x-intercept of any function in the universe? You set the function equal to 0 and solve. All right? Now, find the x and y intercepts of that guy there. Right? Y-intercept. Oh, y-intercept? Sometimes there is no y-intercept. That's a possibility. When you plug in 0, you might get a 0 in the denominator. You plug in 0, you may get a negative under a square root. In those cases, there is no y-intercept. Perfectly acceptable answer. But if there is one, there will only be one. Because if there were 2, it wouldn't be a function. You remember a function is if you pass a vertical line through the graph of a function, it only intersects the graph at most once. If it had 2 y-intercepts, it would intercept twice there. So the y-intercept, f of big fat Greek 0. Right? That's going to be plug in 0. Be careful when you simplify these. What I'll see on test a lot here is 0 over minus 1. Or 2 over 0. Both of those will show up maybe in 20% of the test, one of those two. So 2 over minus 1 is minus 2. X-intercept. Here you're going to solve f of x equal to 0. What's our f of x? X plus 2, x minus 1, that's our function, equal to 0. Now sometimes you can sit and just stare. How do I solve for x there? Very simple property we're going to use over and over again this semester. You ready? A fraction equals 0. Fraction will equal 0 when the numerator is 0 and the bottom denominator is not. Top equals 0, the bottom isn't. So this amounts to x plus 2, the numerator, equaling 0, or x equal minus 2. It's a coincidence that's the same as that one up there. Okay, right? So remember that about fractions. We're going to be using that several times this semester. A fraction equals 0 when the numerator is 0 and the bottom isn't. By the way, if the numerator is 0 and the bottom is 2, it's a different case. It's a different case, right? That will mean, well, that could mean several different things about the graph and the function. In any case, if you have a 0 over 0, if the numerator is 0 and the denominator is also 0, there is no graph at that point. There will be no point on the graph corresponding to whatever number that made 0 over 0. Okay. But in the case that, you see, we got the top being 0, if we put minus 2 in, the bottom will not be 0. That gives me my x-intercept. Yeah, x-intercept. Now, there can be more than one x-intercept. You can have a loopy-droopy polynomial, and it could cross the x-axis any number of times. And we're going to have those. Trigonometric functions. Any of you had pre-calc class? Trig? Sine curve? Right? It intersects the x-axis infinitely many times. Right? But the y-axis only once. Okay? Now, if you put this buzzard on your calculator, notice you put that parenthesis in like I didn't do on that other problem. Right? Put that parenthesis in there. You get the graph. Notice, here, you know what? This is the y-intercept, and we can get the x-intercept too. Right? Let's do one thing. Let's do here. X plus 2, x minus 1. What happened? Don't tell me. Sorry. I didn't put a negative sign in. Dividing sign. Okay. That's the same graph you have on your paper. To get the x-intercept, just plug in 0, minus 2. Y-intercept, second trace, 0 function, enter. Let's type in like minus 4, right? Left bound, minus 1, say for the right bound. It's going to look for a 0 in that interval. Enter again, it gives you also minus 2. So that's just a review of how we got that. Don't want to keep you over. Have a safe weekend. It's not supposed to snow much or this afternoon anyway. So if you have to drive in this, we'll snow in the streets. These bricks right here, if you're New York, these bricks out here, they can get really slippery with just a little bit of snow on top of them. Because those tops of those bricks have been polished. Those brick streets are over 100 years old. Well over 100 years old. So there's some slippery bricks out there. Don't become a statistic. Have fun this weekend. Take care, Microwave. Oh, thank you. Yes, I need to pick that up. Appreciate it.